Hello, my name is Anuj Bhatia, and this is my lab report for Lab 2 Projectile Motion. So an introduction, in this lab we threw an object which is an exo marker in the air and recorded its motion. We then put the video into Tracker to acquire experimental data and also made a computational model of the experiment in closed grip simulating a toss with drag and one without drag. The main purpose of the lab was to observe how forces such as drag and gravity affect the motion and its position, affect the object and its position, to compare the tracker data with the computational model data and to see how accurately physics principles can predict the motion of the projectile. The main result from the lab was that drag and other forces play a large part in the object's motion, which can be seen in the tracker data, because the computational model that included drag predicted the motion of the object much better. So some fundamental physics principles we use in the lab are the position update formula, velocity update formula, gravity, and drag, which will be mostly used in the computational model. Some additional conditions were that the mass of the marker was 0.1 kilograms, the total time that was in air was 0.667 seconds, and the initial position, which is from the tracker data, was 0.211, negative 0.279, 0 meters. The initial velocity, which was calculated using change in r over change in time, was 1.191, 0.313, 0 meters per second. The system was the marker, and the surroundings were gravity, air, which is drag, and the initial force from throwing the marker from our hand. So some experimental details. These pictures show the experiment setup and the tracker data. The meter stick was used as the y-axis for the tracker, and the path that the marker made for each track point of motion can be seen with the red boxes. The top graph shows the position in the x direction versus time, and the bottom graph shows the position in the y direction versus time. So some details of the code. The first chunk of code initializes the sphere object with trail, origin, and arrows, and it initializes the graphs that the model will generate, which is x position versus time, y position versus time, y velocity versus time, and object trajectory. The next section of code initializes the mass of the marker, initial position, initial velocity, initial time, delta t, the value of gravity, and the drag constant, which can be 0 depending on which computational model we are viewing. Some more details about the computational model. The next chunk of code enters a loop till final time, where position and velocity are updated using the position update formula and the velocity update formula for each increment of delta t, while also factoring in the gravitational and drag forces. And the last chunk of code updates the graphs and the ball simulation with arrows at each time increment, and also prints x position and y position data for each increment, so we can compare data after the model is done running. So for the computational model data that we accounted for drag in this model, gravity and drag, which is non-constant, are the only forces that act, and we simulated with a small drag coefficient of 0.02. So you can see in the x direction that there's a slightly curving slope, and in the y direction there's a more skewed parabola. So in the computational model where we didn't account for drag, in which only gravitational force acts, which is constant, we can see a constant and linear slope in the x direction and a fairly even parabola in the y direction. So for some data comparison, we can see that although the difference is slight, the data from the computational model that accounts for drag is much more similar to the data of the actual tracker, because we can see the slight curvature in both, and also the more skewed parabola in the y direction. So as I was saying, the main takeaway from the graphs is that the computational model data that accounts for drag is more accurate when compared to the experimental data, which can be seen because the computational model graph that accounts for drag looks closer to the graph of the real tracker data. And this is because the actual data is also impacted by drag and likely other outside forces as well. Some possible sources of error as to why the tracker and the computational model data aren't one-to-one could be software errors, like errors with tracker, which could be manual or software errors, data errors, measuring or calculating initial conditions inaccurately, and unaccounted outside forces such as drag or friction that couldn't be properly accounted for without more precise tools. Calculations could have caused some discrepancies within the data. So some additional questions. Did any of the models predict terminal velocity? The model that accounts for drag force predicts terminal velocity, and this is because terminal velocity is achieved when the net force of an object in free fall is 0, and the drag force increases as velocity increases, so it will eventually increase to balance and counteract the gravitational force on the object achieving terminal velocity. And for the next question, if I threw the marker straight up, would the time to reach the ground be the same, longer, or shorter than the time it took in the original experiment? Throwing the marker straight up would take longer to reach the ground compared to my initial experiment, and this is because drag can act with full force on both the way up and down when the marker is thrown straight up. Without drag, we can see that the formula for total time in my initial experiment was 2VO sine theta over g, and for throwing the marker straight up, it is 2VO over g, and which is greater than 2VO sine theta over g, because sine theta oscillates between negative 1 and 1. So the time for throwing the marker straight up would be greater than in my initial experiment. And in conclusion, this experiment displayed how forces such as drag force can affect ideal projectile motion, in which there's only a constant force of gravity acting on any given object. The experimental data for when we threw the exo marker as our projectile was much more similar to the model in which we accounted for drag force compared to the one where we did not, which showed that in real life, non-ideal scenario, outside forces do act on our projectile. Thank you.